Hello students, today we are going to discuss about superconductivity. In our previous classes, we have discussed about the properties of superconductors, which include first one is zero electrical resistivity, second one is about its critical temperature, third one is about persistent current, and the fourth one is about critical magnetic field. So today we are going to discuss about the fifth property of the superconductor, which is known as critical current density. Critical current density is denoted by letter JC. Let's see what is this critical current density. Consider a superconducting material in the form of ring. Let this ring be held at temperature below critical temperature, so it is in its superconducting state. Now, if I amount of current is flowing through this ring, and if we keep on increasing this current, it leads to a magnetic field around this ring, and the corresponding field is nothing but H. So H is the magnetic field which is produced around the ring due to the current flowing through the superconducting material. So this I value has some critical value. It can be increased up till the value of IC, above which the material turns to the normal material. So this critical current leads to a magnetic field around this superconducting material, which is known as critical magnetic field. So this critical magnetic field is enough to destroy the superconducting state of the ring. So this critical magnetic field corresponds to critical electric current here. All of us, we know that the current density is always related to the current with the formula I divided by A, where A is area of the specimen or the material. So if IC is the critical current, it leads to the critical current density, that is JC, which is nothing but is equal to IC by A. So this JC is known as critical current density. So we need to take care of the material to be superconducting, as it should not exceed its critical temperature, it should not exceed its critical magnetic field, also it should not exceed with its electrical current density. So I can draw the graph of all these three together, something like this. Let's take temperature on x-axis, let's take the magnetic field on the y-axis, and this is the current density on the z-axis. So this temperature has a critical value which is denoted as Tc. Below this Tc, only the material is superconducting. If you exceed Tc, the material is going to behave as the normal material. Similarly, there is a critical value, as we have seen in the previous video, for the magnetic field also. So below this Hc, the material is superconducting. If we exceed this Hc, material is a normal material. Similarly, due to this magnetic field produced due to the current in your superconducting ring, it gives rise to a critical current density, beyond which if the current through the ring exceeds, the material is going to behave as the normal material. So this corresponds to GC. If I join the points, all these 3 points, something like this, then the material is superconducting only under this shaded area. That is, the material is superconducting here only. If we cross this, the material is nothing but a normal material. Anywhere outside this shaded portion, the material acts as the normal material. Okay, this critical current which is flowing through your superconducting ring, it is related to the critical magnetic field with a formula given as IC is equal to 2 pi R into HC. Critical current is equal to 2 pi into R into HC, where R is the radius of the ring and IC is critical current, HC is critical magnetic field. So this IC is directly proportional to HC and the radius of the ring. Let's see one or two numericals on this formula. Let's take down the first numerical. The critical magnetic field at 5 Kelvin is 2 into 10 raised to 3 ampere per meter in a superconducting ring of radius 0.02 meter. Find the value of critical current. This is a very simple numerical where if we are given with the magnetic field strength, we are given with the radius. We need to find out the critical current. So let's look into the solution of this problem. Write down the given things first. The magnetic field HC is given to us. It is nothing but 2 into 10 raised to 3 ampere per meter. The radius of the ring is given, R is 0.02 meter. We need to find out the critical current, question mark. So all are in SI unit. We can directly use the formula. The formula is IC is equal to 2 pi into R into HC. Let us substitute the values now. 2 into pi is 3.142 and R value is 0.02. HC is 2 into 10 raised to 3. When you multiply these values, you are going to get the answer as 251.4 ampere. This is the simplest numerical. Let's see one more numerical, little bit complicated, where we are going to use this equation and also the equation which we have taken in the previous video. So let's write down the problem first. Calculate the critical current for a wire of lead having diameter of 1 millimeter at 4.2 Kelvin. The critical temperature of lead is 7.1 18 Kelvin and the critical magnetic field at 0 Kelvin is 6.5 into 10 raised to 4 ampere per meter. So let's see the solution of this. Calculate the critical current. So the question mark for IC. Given is diameter D is equals to 1 millimeter. Convert this 1 into 10 raised to minus 3 meters. Okay, we want radius, so radius will be r is equals to d by 2, so it is 0.5 into 10 raised to minus 3 meters. At 4.2 Kelvin, the temperature is given, T is equal to 4.2 Kelvin. Then the critical temperature of lead is given, that is Tc is equal to 7.18 Kelvin, and the corresponding magnetic field is given, Hc of 0 is equal to 6.5 into 10 raised to 4 ampere per meter. But the critical field at this temperature is not given, which is required for this formula. So what we do is we will try to find out Hc at the temperature 4.2 Kelvin. This is the previous equation which we have already dealt. From that equation we know that Hc of T is equal to Hc of 0 into the bracket 1 minus T divided by Tc the whole square, bracket complete. Using this formula, let us find out Hc of T first, then we will substitute in this formula to find out the Ic. Let's substitute the values here. So this is 6.5 into 10 raised to 4 in the bracket 1 minus one more bracket, T is 4.2 divided by 7.18 raised to square and bracket complete. When you simplify this, your answer will be 4.28 into 10 raised to 4 ampere per meter. Now we need to find out the IC. Let's write the equation for the IC. IC is equals to 2 pi into R into HC. Substitute the values. 2 into 3.142 into R is 0.5 into 10 raised to minus 3, which we have found here. Then 4.28 into 10 raised to 4. So when you multiply all these values, you are going to get 134.5 amperes as the critical current. So this is the critical current what we wanted to find in case of this problem. So what we understand from this is the two equations may be combined and the question may be asked. Okay, thank you.